So let's start. We have the first volume here. Can you see that from this line here, there's a volume here called VC. VC stands for the clearance volume. What is the clearance volume? When the piston starts from BDC, compressing the air, BDC stands for bottom dead center. It compresses the air from whatever pressure it compresses. Remember, when the compression takes place, the pressure increases, but the volume decreases. So the volume is going to decrease from BDC, and the piston compresses up until TDC. TDC stands for top dead center. Now you'll be aware that the piston does not move up until this region here. Why? It's because if it passes this region here, it is going to collide with the valves. So the piston must stop at TDC. So the volume at which the piston cannot compress is called the clearance volume, VC. So the VC is the distance from this vertical line to the TDC. Now we have what we call V1. V1 is the total volume. The total volume is going to be the distance from B up to that line. So the V1 is not from here. It's not from this point to that point. It is from B up to that line. So the distance from this point here, the top of the piston up until BDC, is V1. It is called the total cylinder volume. Now the volume that is swept by the piston, in other words, the distance from BDC to TDC, it is called the swept volume, or it is called the stroke volume. Now you always hear people talking about, especially these car lovers, talking about 2 liters, 3 liters, 4 liters. The car is a 3 liter, or is a 4 liter, or is a 2 liter. What does that mean in terms of these volumes? Now, let's say the car that you are talking about is a 2 liter. Now, if you wanted to know which volume is this, now say that 2 liter, first of all, you have to determine the number of pistons or the number of cylinders. If it is a 4-cylinder, now you say that 2 divided by 4, which is going to be 0.5. It means that each cylinder gives 0.5. So we multiply by 4, it will be 2 liters. But the question is, between this VC, V1, or swept volume, which 0.5 is that? So this volume here from BDC to TDC is the volume that we use to calculate the engine capacity. So if we say our car is a 2-liter car, we are going to calculate this volume. We multiply by number of cylinders, it will give us 2 liters. How do we calculate that? First of all, we need the diameter of the piston as well, which is a cylinder diameter, or the bore, cylinder bore. And then we will need the distance from TDC to BDC, which is the cylinder length. So once we have the length and the diameter of the piston here, now we can calculate the volume, which is pi d squared multiplied by L divided by 4, we get the volume. You multiply by 4 cylinders, you will get your 2 liter. So sometimes in the question will say, for a 3.5 liter car with the 4 cylinders and the cylinder length of well, let's say 350 millimeters, calculate the diameter of the cylinder. So this is how we get to this. So the volume, this volume here from TDC and BDC, is the one that we use to calculate the capacity of the engine. Now let's move on. If you look at this case here, I'm saying that this is an actual PV diagram of an internal combustion engine. Now the question is, if you want to calculate the engine performance or other variables of the engine, how can we calculate? Is there anything that we can obtain from this particular sketch? The answer is no. This sketch is so complicated that we can't make sense of anything, because you look at all of these lines, you can't do anything with this sketch here. In other words, it's useless. So with the actual one, there is no way in which we can get any useful information. So for us to get what we want from this particular sketch, we have to simplify it. Now, when we simplify this particular sketch here, we get what we have on the right-hand side, which is an ideal or a theoretical PV diagram of internal combustion engine, in other words, a petrol engine. So the difference between these two PV diagrams is that the one on the left is the actual one. The one on the right is the theoretical one or the ideal one. The reason why we have to develop the one on the right is because it is physically impossible to make sense of what is happening. If we have to calculate the work net here, we can't calculate it. We want to calculate the heat rejected or the heat input. We can't do anything because this sketch is so complicated. So hence we have to do what? Simplify it. So this particular point here from CD is going to be represented here by 2, 2, 3. Now this point from EVO up to that point here is going to be Q out, and the compression from B up to C is represented here by a compression process from 1 to 2, and the expansion is between 3 and 4. But when we do that, we move from the actual one to the theoretical one. We have to make assumptions because in engineering, some of the problems are so complex and complicated, they cannot just be solved. One example is this one. So we have to make what do you call it, the assumptions to move from the actual one to the ideal one. So the assumptions that we make here are called air standard assumptions. And those assumptions are four of them. So the first assumption is that the working fluid is air which continuously circulates in a closed loop and always behaves as an ideal gas. This is not true, but we have to make an assumption that the working fluid here is air and is continuously circulating through the loop. But in actual fact, it's not a loop because at some stage the valves will open and allow fresh air to enter the system. So this is just an assumption that we have to close this, make it a cycle in order for us to be able to solve the problems. Now, the second assumption is that all the four processes that make up this cycle are internally reversible. Okay, internally reversible, okay, in theory, yes, we can say that the processes are internally reversible, but in actual fact, practically, there's no processes that are internally reversible, but we have to make that assumption. The third one is that the combustion process is replaced by the heat addition process from external source. Now let's go back to that sketch again. We say that the combustion process is taking place here between C and D. This is when the spark plugs ignite. The fuel mixture to combust or to burn the fuel. So because you don't have that is represented by QE. Instead of combustion process, we have heat addition at constant volume. That is another assumption. Now, assumption number 4, we say that the exhaust process is replaced by heat rejection process that restores the working fluid to initial states. Again, this is not true because remember, between EVO and that point here is when the piston, the valve opens to allow the mixture to leave the chamber. But in this case now we say, no, we are not going to have that because this is a closed loop. We replace this with a constant volume heat rejection. So this is another assumption. Now the last one, we say that another assumption that is often utilized simply to simplify the analysis even more is that the air has a constant specific heat determined at 25.25 degrees Celsius. In other words, we assume that the specific heat capacity of air, Cp, is 1.005, Cv is 0.718 at 25 degrees Celsius. But as the temperature increases to 30, to 35, to 50, to 100, they don't change. We assume that they are still the same. Hence, you find that Cp and Cv, they are always the same, even if the temperature is more than 25. But actually, the Cp and Cv are 1.005 and 0.718 at room temperature, which is 25. As the temperature increases, in actual fact, they do increase as well, they do change, but we assume that they remain constant. Those are the standard assumptions that we make when we move from an actual cycle to a theoretical one. Now, this slide is unnecessary. Internal combustion engine. Okay, so what is the difference between an internal combustion engine and external combustion engine? The difference is simple. In internal combustion engine, a working fluid is allowed to mix with fuel. Like in internal combustion engine, the working fluid is air. It mixes with petrol or diesel in order to oxidize. So this is, in other words, there's a chamber. In the chamber, they are taking the oxidation or combustion is taking place in the same chamber. But in external combustion engine, like in a steam plant, a working fluid is steam, but steam does not mix with fuel. So we have a different combustion chamber, which is the combustion is taking place externally, not internally, unlike in the internal combustion engine. So the example of external combustion engine is a power plant. The internal ones is cars, locomotives, airplanes, and so forth. Now, let's have a look at this. This is what was explained in the video earlier on. What we have here, we have a cylinder and a piston arrangement. Now, the diameter of the cylinder is called a bore. The length, you can see here, is a bore. That is the diameter. In other words, you find that when you're asking the question, we will not say that the diameter of the cylinder is this much. We'll say that the bore is, let's say, 30 centimeters or 350 millimeters. And the stroke, we won't say that the length of the cylinder is this much. You say that the stroke is this much. So what is happening here, you see that the piston is going up and down. I said that BDC stands for bottom dead center, TDC stands for top dead center, and the piston will go up as it goes up to this point here. It will not go up until this point here because it's going to damage or it's going to collide with the valves. And this volume here, that is cannot be swept by the piston, is called a clearance volume. So let's have a look of what is happening on the right hand side of the sketch. We have 4 cylinders with 4 processes. The first process is the intake. During the intake, the piston is going down, and as it goes down, it creates the vacuum, and that vacuum also opens or pulls the valve, and it opens and it allows the air to enter the system but the pressure must be always less than atmospheric pressure, because if the pressure is the same, then it won't be able to enter. So it creates a vacuum to allow air inside the cylinder up until this point here. Now, when the cylinder is full of air, now we go to compression. The compression takes place. It goes up, it compresses up until somewhere here, up until TDC. It doesn't go up to this point here, up to TDC. So when the piston is at TDC, the spark plug is going to initiate the spark. In other words, the power stroke. Now remember, this air here at that point is highly compressed. And when it's highly compressed, the temperature is also at the highest. Now just the spark plug will reach just one spark, and then it's going to ignite. As it ignites, it's going to explode. As it explodes, it will push the piston down. This is the power stroke. The piston goes down. Now it gives the motion to the crankshaft. Now, when it's at the bottom dead center now, these exhaust gases, they must leave the cylinder. Now we move on to the exhaust process or stroke. Exhaust, now the piston is going up to discharge all the air, not all the air, because there will be a little bit of air that is left in this, not all of it will go out. And then it pushes up until this point here. When all the air is out, it will close and the process will jump to point number 1. So in a motor car engine, I'm sure you always hear people talking about the firing order. So the firing order of this piston here is normally, the normal firing order, I think, is 1, 3, 4, 2. 1, 3, 4, 2, it means that the first cylinder that is going to fire is going to be the first one, followed by number 3, followed by number 4, followed by number 2. So the question that I'm asking you, you don't have to answer me now. What will happen if all in a motor car engine, if all the cylinders have to fire at the same time? Or what will happen if the movement of these 4 pistons has to be the same? They go down at the same time, they go up the same time, they fire at the same time. What will happen to a motor car if that is the case? You don't have to answer me now. Think about it. But normally, most cars, they fire in order for a 4-cylinder engine. It is 1. After firing, it is followed by number 3. After firing, followed by number 4, followed by, 1, 3, 4, 2. Yes. But the firing, it can always change. It's not constant, but normally the first one must always fire first. So what happens thereafter? But the normal one that we always know, that you already know, is 1, 3, 4, and 2. So my question is, what will happen if the 4 cylinders are to fire at the same time or are to go up or down at the same time? You don't have to answer me that question. Right. So I think this slide is actually a repetition of what we have done. What I'm not too sure about is this temperature entropy chart diagram, because I'm not sure if Mr. Pietrangeli did explain or cover this topic with your TS diagram. Because for every PV diagram, there must be a corresponding TS diagram. Why is it so important? It is important because when you calculate your temperatures, you know that according to this sketch here, if this sketch is correct, your temperature number 1 is the lowest temperature in the cycle. And the question sometimes will say that it won't say T3 is this much, you say that the highest temperature in the cycle is this much. So this sketch tells us the highest temperature here is number 3. So when you do your calculations, you calculate T2 and T3, you'll find that your T2 is greater than T3, then you know you made a mistake. But now if you don't have this sketch, you won't even see or recognize that mistake. Similarly, what I said is that you must always draw your PV diagram. The PV diagram will tell you the pressures and the volumes. You know that the pressure at point 1 is less than the pressure at point 2, but the maximum pressure is P3. So when you do your calculations, you know that your answers must correspond, must make sense when you put them on this particular sketch. Now for temperatures, we have to use that one. So I'm not too sure if Mr. Pietrangeli did cover the TS diagram for all the processes. Remember, the processes is what? Constant volume, constant pressure, constant temperature, polytropic, and adiabatic. So all those 5 processes, they have corresponding TS diagrams. So this is an Otto cycle. An Otto cycle consists of 2 constant volumes, which is V1 here is equal to V4, and then V2 is equal to V3. So the heat addition takes place between a constant volume between 2 and 3, and the heat rejection takes place between 4 and 1. So the compression ratio of this cycle, Otto cycle, is V1 over V2. That is the compression ratio. The expansion ratio is going to be V4 over V3. This is important, ladies and gentlemen. I'm saying that the compression ratio of this gas is that V1 over V2. And then the expansion ratio is going to be V4 over V3, because V1 is equal to V4 and then V2 is equal to V3. Now again, you can see here there is a clearance volume here. You can see this volume here is not touched by the cylinder. So the length traveled by the piston is called the swept volume or the stroke volume. So the piston swept this volume from 1 up to this VC here, which is V1 over V2, where the pressure increases and the volume decreases. That is during compression. During expansion, the same happens, but in reverse. The pressure drops, but the volume increases. So this is called an Otto cycle, or a petrol engine cycle, or a spark ignition or SI cycle, consisting of 4 processes: compression, constant volume heat addition, expansion, constant volume heat rejection. That's all we have. So we move on now to the efficiencies. The efficiency of all the cycles is the same, all of them. It doesn't matter which cycle, but it's the same, which is what, according to the first law, is going to be work net. Sometimes I use work net, sometimes I use work out. It's the same thing. which is work out divided by Q in. Now, for a cycle, we know that Q in minus Q out is equal to work out. This is according to the first law. So if you want to continue from there, you can say Q in divided by Q in is going to be 1 minus Q out is between 4 and 1. Q in is between 3 and 2. All of this mass and the CV, because the heat rejection and heat addition takes place at the constant volume, they will cancel. So our final answer is going to be the efficiency of Otto cycle is 1 minus this. This is our final one. But sometimes in the exam, we find that you don't have to use this particular, when the question says calculate the efficiency, you find that you have to calculate T2, T3, T4. And in that process, you can make a mistake, because if your TT is wrong, it's going to affect T3, it's going to affect T4. So there's a shortcut to this. But now, shortcut to this, we have to do some mathematical manipulation in order to get to the shortcut of this formula here, which is the same as that one, but it depends on what we have. If we have all the temperatures, you can use this formula. But if you don't have temperatures, now we use this particular formula here. This is what we have. But what I have done here, I just wanted to show you that sometimes you forget how, you don't know how to get to this point here. In class, I can easily derive this one, but this is not the purpose of the lecture, is to teach the students to derive. No, is to understand where the formula is coming from. Because in thermodynamics, almost all the formulas there can be derived from first principles. So this one I can easily derive, I can get to this one. So I don't have to memorize that, oh, Otto cycle is 1 minus. No, I don't have to. So unfortunately, the textbook uses K. I don't use K, I use gamma. Gamma is a ratio of Cp and CV. So when the question says Otto cycle calculate the efficiency, all you need to do is 1 minus 1 divided by compression ratio, gamma minus 1. You will get the same answer as when you use the temperatures. So when you have time in the problems that we're going to solve, I'm going to use this one because we won't have enough time to calculate all the temperatures. When you have time, calculate all the temperatures, use that one, you'll still get the same answer as when you use the second one. So this is the theoretical efficiency of an Otto cycle, where gamma is, where K, I use gamma, not K, but the textbook uses K. It's up to you. I don't care which one you use. You can either use gamma or you can use K. It's up to you. The second cycle is the diesel cycle. Now, from that, the video that we have watched, we know what the diesel cycle is, the difference between it and the petrol cycle. So, diesel cycle also consists of 4 processes. The first process here is the compression process between 1 and 2, compression. Now, between 2 and 3, Q in. Remember, in the Otto cycle, heat is added at constant volume. But for diesel cycle, heat is added at constant pressure. In other words, P2 is equal to P3 for a diesel cycle. And then we have expansion and you have a heat rejection at constant volume. So the difference between diesel cycle and Otto cycle is that Otto, the heat is added at constant volume, but for diesel cycle, heat is added at constant pressure. That is all. And then we have what we call the cut-off volume or cut-off ratio. The cut-off ratio is the ratio of the volume at 3 and the volume of 2. In other words, going to be V3 over V2 is called volume cut-off ratio. This is at this point where is when heat is added up until 3, and then you cut the heat at 3. So the volume at 3 divided by the volume of 2 gives us what we call the fuel cut-off. And then again, if we move on to the efficiency, we can say that the efficiency for a diesel cycle is going to be 1 over gamma T4 minus T1. But again, if you don't want to go, this route of calculating temperatures, there's the easy formula that you can use. Again, you can easily derive this formula, but like I said, that this is not the intention of this session now to teach students how to derive. But the final answer It's either you can use this one or you can use that one. It depends on what you have. If we have temperatures, you can use this one. If we have the pressure ratios, you can use this one. So what it says that is 1 minus 1 over pressure ratio, gamma minus 1 bracket. This is a cutoff ratio to the power gamma minus 1, and then a gamma bracket cutoff ratio minus 1. So yeah, I think that's it. The last one is going to be Joule cycle. Joule cycle has got so many many names. One of the names is Joule cycle. The other one is a combined cycle. The other one is what? It's quite a lot. It's quite a lot. Quite a lot. So, what is a Joule cycle? Joule cycle is actually a diesel cycle, but it is meant for this fast, efficient engines. Remember, the cars these days, diesel cars. Remember, in olden days, we used to have complained that diesel cars are very slow and blah blah. The performance is not that good. They are strong, but they are very slow. But nowadays, you have powerful diesel cars. Diesel cars is because they use a dual cycle. What is the difference between dual cycles and other cycles? Dual cycle actually combines both diesel cycle and Otto cycle. You can see that for dual cycle, heat is added at both constant volume and constant pressure. So what it does, it combines. If you draw a line from 3 to 5, it becomes an Otto cycle. If you draw a line from 3 to 1, it's a diesel cycle. So a dual cycle is actually a combination of both Otto cycle and diesel cycle. Now again, the efficiency here, there's a whole lot of things that you haven't seen before. The first one is RC compression ratio, gamma minus 1. This is what? This is a pressure ratio. The pressure ratio is going to be P3 over P2. Pressure ratio multiplied by cutoff ratio, gamma minus 1. This is pressure ratio minus 1, gamma multiplied by cutoff ratio, gamma minus 1. But we will explain this when we do examples. All you need to do now is just have to, do you have to memorize this? No, I think in the exam, we give you these formulas as well for mid-year test. So there's no need for you to memorize. But for now, what I know is that you can calculate the pressures, you can calculate the volumes, you can calculate temperatures. Another importance of a TS diagram. Can you see now in this TS diagram, now we have 5 temperatures, T1, T2, T3, T4, and T5. So if you draw this sketch when you're answering the questions, now you know that T5 is slightly higher than T2. And then T3 is between T5 and T4. And T2 is just over. So it helps you to check, for you to be able to check your answers, whether your answers do make sense or not. Just like on the other side here, that you have P2, which is less than P3, and P3 is equal to P4, so forth and so on. So yeah, this is very, very important. For every question that you answer in the exam, please draw both PV diagram and TS diagram. So from this sketch here, 1 to 2 is isentropic compression. I don't want to deal much with that because I can see that Mr. Pinagel did not really cover this section here, but just teach you to memorize or to show you how it works. Because between 2 and 3, the volume is constant, that is V is equal to C. Between 3 and 4, the pressure is constant, that is why we say P is equal to C. And again, between 5 and 1, volume is constant, why we have V is equal to C. But yeah, this is, you just have to memorize the TS diagram because we did not cover that in class last week. So there's another concept here called the mean effective pressure. So the mean effective pressure is actually used to compare the engines, the performance of engines, similar engines. You can't use MEP to compare difference or the performance of different sizes. So what is MEP? The MEP is actually during the power stroke, there is an average pressure acting on top of that piston that is pushing the piston back to where it was in the beginning. The pressure, the average pressure that is acting on top of that piston, it is called the mean effective pressure. An average pressure acting on top of the piston during the power stroke is called the mean effective pressure. The mean effective pressure here, you can see from this sketch here, we say this area here, work net is equal to MEP multiplied. This area here is the work net. This area is equal to that area. So work net is going to be the mean effective pressure multiplied by V1 minus V2. That is the mean effective pressure.